So now we are going to see the solutions of operating system questions from GATE 2022 examination. Okay. As part of that, first question from the operating system here, this is the question statement, like consider a demand paging system with 4 page frames initially empty and LRU page replacement policy for the following page reference string. So what is the given following page reference string here? 72732534677151. The page fault rate defined as the ratio of number of page faults to the number of memory accesses rounded off to 1 decimal place is dash. So here it is mentioned that this is the given page reference string, and it is clearly mentioned that the memory is having 4 page frames and we are using LRU page replacement policy. So these are the highlighted things here, right? So now look at, so first let us consider the page reference string here. So first if we consider the page reference string, so what is the page reference string we have? 72732534677156 and 1. So this is the given page reference string to us, right? And what is the number of page frames in the main memory? That is 4. So it means that initially the memory is having 4 page frames. There are 4 page frames and which are empty initially. Okay, right. So now we are using the page replacement algorithm called LRU here to find out the page fault rate here. Okay, right. So now CPU is willing to access page 7 here. But page 7, is it there in the main memory currently? No. So it means that we need to bring this particular page 7 into the main memory for the CPU access. So since this particular page 7 is not part of main memory currently, we can say that it is leading to a page fault and we are bringing that page 7 into the main memory. So now this is page fault here. Now the CPU is willing to access page 2, but page 2 is not part of currently main memory. We have only page 7 but we don't have page 2. So that which is leading to page fault, right? So this is leading to page fault. So now 7 is there already in the main memory. Just now we are bringing this page number 2 into the main memory, page 2 into the main memory, right? So now the CPU is willing to access page 7. So but page 7, is it there in the main memory or not? Yes, which leads to page hit. Means in main memory we have at this stage also we have these are the 2 pages, right? Next, now the CPU is willing to access page 3. But page 3, is it part of currently main memory? No. It means that it is resulting a page fault. So now this is a page fault result, right? And we are bringing that particular page 3 into the main memory like this. So now page 3 is part of main memory. Now CPU is willing to access page 2. But page 2 is already there in the main memory or not? Yes, it is there. So which is resulting a page hit. So now page hit is resulted. So 723. So now the CPU is willing to access page 5. So but page 5 is not part of currently main memory. So which means that we need to bring this particular page 5 into the main memory due to the result of page fault, right? So now we are bringing this particular page 5 into the main memory because it has created some page fault. So now 7 is there, 2 is there, 3 is there, and just now we have brought that particular page 5 into the main memory. Okay, right. Now the memory is full. Okay, so now coming to this, now CPU is willing to access page 7, page 3, right? Page 3, but page 3 is already there in the main memory, so that it is resulting a page hit. So now 7, 2, 3 and 5, it is a page hit. So now the CPU is willing to access page 4. But page 4, is it part of currently main memory? No. And are we have any empty location in the main memory? No. Then among these 7, 2, 3, 5, one page must be selected for the replacement by this particular 4. As we are using LRU, which is least recently used page replacement algorithm, among the 7235, which is the least recently used? Have a look. So if you verify, 3 is the most recently used. After 3, 5 is the next most recently used. After 3 and 5, 2 is the next most recently used. Comparatively, 3, 5, 2, 7 is the least recently used, so that 7 is the victim for the replacement here. So it means that 7 gets replaced by 4, and this is a page fault. Now the CP is willing to access page 6, but page 6 is also not part of currently main memory. Then among this 4 to 3, 5, one page we must select for the replacement. So among the 4 to 3, 5, if we verify, 4 is the most recently used. After 4, next most recently used is 3. After 4 and 3, the next most recently used is 5. So comparatively 4, 3, 5, 2 is the least recently used, so that 2 is the victim for the replacement here. So 2 will be selected for the replacement by 6, and 4, 3, 5 can continue here. So this is also a page fault. Now the CP is willing to access page 7. So is page 7, is it part of the current main memory? No. Then among the 4, 6, 3, 5, one page must be selected for the replacement. But which page needs to be selected? Have a look. 6 is the most recently used. After 6, 4 is the next most recently used. Compare after 6 and 4, 3 is the next most recently used. Comparatively 6, 4, 3, 5 is the least recently used. So 5 will be the victim for the replacement here. So it means that this 5 can be replaced by 7 now. So then 7, 3, 6 and 4, this is also a page fault. So now the CP is willing to access page 7. But page 7 is already there in the main memory, which is resulting a page hit, and the memory pages are 4, 6, 3 and 7. So now the CP is willing to access page 1, but page 1 is not part of currently main memory, which is resulting a page fault. So now it is resulting a page fault. But among the 4, 6, 3, 7, which page will be selected for the replacement? Look at 7 is the most recently used among the 4, 6, 3, 7. 7 is the most recently used. After 7, 6 is the next most recently used. After 7 and 6, 4 is the next most recently used. Comparatively, 7, 6 and 4, 3 is the least recently used. So the 3 will be selected for the replacement. So 1, 6, 4 and 7. Now the CP is willing to access page 5. But page 5 is not part of current main memory, so that it is resulting a page fault. And among the 4, 6, 1, 7, which page will be selected for the replacement? Verify. 1 is the most recently used. After 1, 7 is the next most recently used. After 1 and 7, 6 is the most recently used. After 176, it means that comparatively 176, 4 is the least recently used. So that 4 will be selected for the replacement by 5. So then it is 5, 6, 1, 7. Now the CP is willing to access page 6. Page 6 is already there in the main memory, so that it is resulting a page hit. So 7, 1, 6, 5. Now the CP is willing to access page 1, but page 1 is already there in the main memory, which is resulting a page hit. So then 7, 1, 6 and 5. So now if we verify the number of page faults. So how many number of page faults we have a look here. So we are having the page fault number 1 here. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8 and this is 9. So total we are having 9 number of page faults. So therefore number of page faults is equals to number of page faults is equals to 9. But it is asking that the ratio of number of page faults to the number of memory accesses. What does it mean? So therefore, the page fault ratio is equals to page fault ratio is equals to number of page faults by number of memory accesses. Number of memory accesses. What is the meaning of memory accesses here? Memory accesses in the sense simply number of page faults plus number of hits. Number of page faults plus number of hits. The meaning of these memory accesses in the sense number of page faults plus number of page hits. Number of page faults and number of page hits. So this is what your number of memory accesses. So now what is the number of page faults here? 9. And how many number of page faults again we are having? 9 plus number of page hits. How many page hits we have? Have a look. 1, 2, 3, 4, 5 and 6. So total we are having 6 number of page hits. So then it is 9 by 15. So if we evaluate this, we are going to get 0.6. So 0.6 is the ratio of number of page faults to the number of memory access, which means that indirectly it is asking that the page fault rate. So the page fault rate is 0.6. So 0.6 is the answer for this question. Okay, right. So now we are moving to next question. So this is the question, this is the next question we have from operating system in GET 2022 examination. Look at this question statement. Consider 4 processes P, Q, R and S scheduled on a CPU as per round robin algorithm with a time quantum of 4 units. The processes arrive in the order P, Q, R, S all at a time t is equals to 0. There is exactly one context switch from S to Q, exactly one context switch from R to Q and exactly 2 context switches from Q and R. So this is the critical line of the question statement. This is the critical line of the question statement. There is no context switch between S and P. There is no context switch from S to P. Switching to a ready process after the termination of another process is also considered as a context switch. Which one of the following is not possible? Which one of the following is not possible as CPU burst time of these processes? So option A, it is given P4, Q10, R6, S2. Option B, it is given P2, Q9, R5 and S1. Option C, it is given P4, Q12, R5 and S4. And option D, it is given P3, Q7, R7 and S3. So this is what the critical line. So we have to ensure there should be one context switch between RQ, there should be one context switch between S to Q and there should be 2 context switches between Q and R. This we have to verify. Okay, right. So now look at, so first we are considering option A. What is option A we have? What is option A we have here? So option A, it is saying that the 4 processes, we are having process ID, arrival time and burst time. Process ID is P, Q, R and S. Arrival time, it is clearly mentioned that all are arrived at time 0. So all are arrived at time 0 but in the same order P, Q, R, S. And the burst time, according to the option here, the burst time is P burst time is 4, Q burst time is 10, 6, R burst time is 6 and S burst time is 2. So then we are going to apply round robin scheduling algorithm on this particular system. So and it is clearly mentioned that the time quantum is 4. Okay, right. So now let's consider ready queue. Ready queue. So into the ready queue, these 4 processes are arrived in this order P, Q, R, S. They are arrived in this order P, Q, R, S. Right. So now let's draw the Gantt chart for this system. So coming to the Gantt chart for this system, at 0, PQRS, all the 4 processes are in the ready queue, but among them which is the first process? P. So that we are handovering this P to the CPU and it gets executed till 4 units because the time quantum is 4 and of course the burst time is also 4. So with this execution, P is finished. So that P is finished, no need of adding this P back to the ready queue. Then among the multiple processes of the ready queue, Q is the first process, so that we can hand over to the CPU. So this will be executed till 8. So what is the burst time of the queue? 10. Among the 10, 4 is executed here, so still it is having 6, right? So now still it is having 6, which means that this queue is not yet finished, right? So means it is again adding back to the ready queue. Now in the ready queue we have the processes R, S, Q. Among them R is the first process, so that we will hand over this R to the CPU. And what is the execution time of R? 6. Out of 6, 4 units gets executed here. So with this execution, is the R is finished in the sense? No. Means that again this R should be added back to the ready queue like this. So with this execution, R is still pending with 2. So now the CPU, now this, if you verify the ready queue, the first process we are having in the ready queue is S. So that S will be execute now. So what is the execution time of S2? 2. So it means that it is going to be executed till 14. And with this execution, S is finished? Yes, S is finished. Now we have Q as the first process. So now this Q will start its execution and it will be executed till another 4 units, that is 18. So with this 4 units of execution out of 6, still 2 is remaining and means that this Q again should be added back to the ready queue here. Now we have in the ready queue R as the first process. So this R, what is the execution time of, remaining execution time of R? 2. So those 2 units gets executed here till 20. So with this execution R is also finished. Then we have only one process, that is Q. So Q is pending with how much burst time? 2. So that 2 gets completed now. So this is the way how you can draw the Gantt chart for this system. Okay. So now look at the number of context switches. So number of context switches, if you verify, number of context switches. So number of context switches between S and Q. Number of context switches between S and Q, if you verify, between S and Q you have only one context switch here, right? Then it is 1, fine. And the number of context switches, between R and Q. So between R and Q, how many number of context switches it is given? One context switch. Look at between R and Q, we have only one context switch. Right? And the number of context switches, between Q and R is equals to. So Q and R, if you verify, here you have one context switch and here you have another context switch. So means that between the Q and R we are having 2 context switches, and even it is also mentioned the same. The number of context switches between Q and R is 2. So the given requirement is satisfied by this option A. But according to this, it is mentioned that which one of the following is not possible, we have to consider. But with option A, all these specified context switches and the corresponding count is possible. So hence option A is not an answer for this question because it is making possible. Then we are moving to option B. So what is this option B? Have a look. So now coming to the option B, it is mentioned that What is the execution time of all the 4 processes that we have to list out first? PID, arrival time and burst time. So PQ, R, S, all are arrived at time 0. Then what is the burst time? So burst time of all 4 processes is 2951, 2951, right? So 2951. So now we are going to do the Gantt chart implementation. Before that we have ready queue. And then we have Gantt chart. So first, these 4 processes are arrived into the ready queue in this order. It means that P is there, Q is there, R is there and S is there. So now the Gantt chart implementation is going to be started. At 0, what is the first process we have in the ready queue? P. So that P will hand over to the CPU. It gets executed how much time? What is the time quantum? 4. But what is the execution time of P? 2, which is less than the time quantum. So means that it can execute till 2 and there is no need of adding back this P to the ready queue. So now we are having the ready queue QRS. Among the QRS, Q is the first process we have. So that Q will hand over to the CPU. Now this will be executed till 6 because its time quantum is 9. Out of 9, 4 units gets executed as the time quantum is 4 and remaining it is having 5 time units. Then means that this queue again we can add back to the ready queue because it is not finished. Now we have the first process in the ready queue is R. So this R will start execute now. It gets executed till 10. And with this execution, is the R is finished in the sense? No, because from 6 to 10 means 4 units only over, means out of 5, if 4 units are over, still it is pending with 1 unit. Now, this R again can be added back to the ready queue here. Okay, so now we are having S is the first process in the ready queue. So what is the execution time of S? 1. It gets executed till 11. And with this, S is finished. Then what is the next process we have? Q. So now Q will start its execution. So this Q will be executed till what time? Another 4 units, means till 15. With this execution of Q, among the 5, 4 units is over, still 1 unit is remaining. And this Q, as still it is having some remaining burst time, it needs to be added back to the ready queue here. Now the CPU is, what is the first process in the ready queue we have? R. So now R will start its execution. This R will be executed. So here already 4 units is over, still it is remaining with 1. So that 1 unit gets executed here. And with this execution R is also finished. So now we have only one process, that is Q, which gets executed 17, right? So this is the way how you can build the Gantt chart for this system. So now verify the number of context switches. Number of context switches between what is the question it is mentioned? RQ1, SQ1. Between R and Q is equals to 1. So verify between R and Q, are we have only one context switch or not? So here we have one context switch. Next, the number of context switches between S and Q. So between S and Q, we have only one context switch here, only one context switch. And number of context switches between R and Q, or Q and R, is equals to. So verify between Q and R, the number of context switches are, here you have 1 and here also you have 1. So means between the Q and R we have two context switches. So these are all exactly given by the question statement, means option B is also satisfying the requirement of the question statement. So that option B is also not possible CPU burst time of these processes. Then we are moving to option C. So what is that option C it is saying? So we have option C, process ID, arrival time and burst time. P, Q, R, S, arrival time is 0, 0, 0. And what is the burst time of PQRS? 4, 12, 5, 4. 4, 12, 5, 4. 4, 12, 5 and 4. Right. So now look at ready queue. So coming to the ready queue, all the 4 processes are arrived in the ready queue in order. What is that order? PQRS. Now look at the Gantt chart. So what is the Gantt chart implementation? Have a look here. So first at 0, we have P as the first process in the ready queue, so that we are handovering this P to the CPU. So then this will be executed till how much time? 4 units. And its time quantum is 4 and its execution time is also 4. So that until that time quanta P gets executed. With this execution, P is finished. Again, no need of adding back this P to the ready queue. Then among the ready queue process, Q is the first process we have. So this will be executed till 8. So with this execution, is the queue is finished in the sense? No. Out of 12, 4 units is over, still it is having 8 units of pending. Then and since this queue is not yet finished and still it is having some remaining burst time, it needs to be added back to the ready queue like this. So now the first process we are having in the ready queue is R. So this R will be executed till 12. It means that out of 5, 4 units is executed now, still it is having 1 unit of execution. So and means that this R again can be added back to the ready queue as it is finished, as it is not finished. Now the first process in the ready queue we have yes. So this S will be executed till 16 because with this 4 itself it is completing, means within one instance, right? So means no need of adding back this S to the ready queue. So then what is the first process we have in the ready queue? Q. So now Q can start its execution, gets executed till 20, right? So till 20. And with this execution is the queue is finished in the sense? No. Again, it needs to be executed. So means this queue should be added back to the ready queue. Now the first process we have in the ready queue is R. So this will be executed. What is the execution remaining execution time of this R? Only 1 unit. So means till 21 it gets executed. And with this execution is the R is finished in the sense? Yes, R is finished. So that no need of adding back this R back to the ready queue. Right. So now the first process we are having in the ready queue is Q, and this will be executed now till 25. Till 25. Right. So now look at the number of context switches. According to the question, it is saying that the number of context switches between R and Q is 1. Between R and Q, it is 1. Look at next. Number of context switches between S and Q is 1. Between S and Q, you have only one context switch? Yes. The number of context switches between Q and R is 2. So verify. Here you have one context switch and here we have one context switch. So which is exactly satisfying the requirement here. So means that option C is also not an answer for this question. So what else remaining now? If we ignore this option C is also, then what else remaining? Option D. Verify option D how it is. So coming to the option D, PID, arrival time, burst time, P, Q, or yes. Arrival time is 0, 0, 0, 0. And burst time according to the option D it is 3773. 3773. So now we are going to draw the ready queue for this. And the Gantt chart building also. So as the question is clearly mentioned that PQRS are entered into the ready queue in this order, that is PQRS. Now if we draw the Gantt chart for this system, among the 4 processes, P is the first process in the ready queue, so that we are handovering this P to the CPU. It gets executed till what is the execution time of P? What is the execution time of P3? So till 3 it gets executed. With this execution, P is finished. Then we have Q. Okay, Q. So this Q can be executed till 7. And with this execution, is the Q is finished in a sense? No. But Q burst time is 7. Out of 7, 4 units is over. 4 units is over. Still, it is remaining with 3 units. Means that this Q can be again added back to the ready queue. So now we have in the ready queue 3 processes, that is RSQ. Among this RSQ, R is the first process we have. Right? So this R, what is the execution time of R? 7. So means till 7 this R gets executed. After that again this R can be added back to the ready queue here. Now in the ready queue we have the first process, that is S. S will be executed. What is the execution time of S? 3. So till 13 this S gets executed. So with this execution S is also finished. Now the first process we are having is B. So this will be executed. So what is the execution time of B? Remaining 3 units. So those 3 can be executed now. So you can say that this is not B, this is, you can say that Q. Okay. So this will be executed till what time? Already this is executed 4 units here, remaining 3 units here, 16. With this execution Q is finished. There is no pending amount here, right? So pending burst time here. Next, we have the next process, we have R. So coming to the R, if we verify, R previously it has executed 3 units here. I mean for the here how many units it has been executed? 7 plus 4, right? So 7 plus 4, 11, and this is going to be executed till 14. Okay, and this Q is going to be executed till 17. So now from 17, so already this is executed for 4 units. So still it is having 3 units of execution. Those 3 units of execution gets executed now, 20, right? So this is the way how you can draw the Gantt chart for this system. So now verify, according to the requirement, the number of contacts switching between Q and R is 2. Between Q and R, if we verify, number of contact switches are 2. It is satisfying this. And number of contact switches between S and Q is 1. Look at S and Q between, we have 1. And number of contact switches between R and Q. Look at, we don't have any contact switch between R and Q. So this option D is failing in creating the contact switch between R and Q. So means with option D, getting this number of contact switches is not possible. So that is why option D is the answer for this question. It is failed, that option D is failed in generating the contact switch between R and Q. Okay. So hence the answer for this question is option D. So I believe you are clear with the explanation of this question. Let's move to next question. So this is the next question we have from operating systems in GATE 2022 examination based on inter-process synchronization. Have a look. Look at the question statement. Consider the following threads T1, T2, T3 executing on a single processor, synchronized using 3 binary semaphore variables, that is S1, S2 and S3, operated upon using standard wait and signal. The threads can be context switched in any order and at any time. Which initialization of the semaphores would print the sequence of BCA, BCA and BCA? So BCA, so the output string is started with the B. So among the three processes, three threads, which thread is printing B? Thread 2. Okay, so thread 2 is printing B first, and according to the output string, B only first printed first, correct? B only have to be printed first, and remaining C and A should be halted, means blocked. So means that in order to allow only T2 to print B first, we need to block S1, T1 and T3 here. Okay, but how can we block them? By performing some wait operation. But the wait operation can be successful on S3 value when it is 1. If S3 value is 1, wait operation can be successful. So then to make this wait operation is unsuccessful on S3, compulsory this S3 value should be 0. Then if before this T2, if T1 tries to execute, it is going to be blocked in wait operation only. It cannot go to C. Okay, so means that this S3 value should be 0. Next, the same way, we don't allow this T3 to print A. So if I want to block this T3 from printing A, compulsory this S2 value should be how much? 0 only. Because when the S2 value becomes 0, this wait operation is going to be unsuccessful. This wait operation is going to be unsuccessful. So it means that T3 also gets stuck here, means it is also unable to print A first. So, but when it comes to T2, since the output string is asking to print first B, compulsory this S1 value should not be 0, it should be something like 1. It should not be 0, that's it. So, when it is not 0, then this wait operation can be successful and then it can print B. After printing, it is making signal on the S3. What is the S3 value? 0. So now B is printed so far. Now it is incrementing the S3 value, which results the S3 value becomes 1. Then it is performing wait operation, which is going to be successful. So after successful, it is coming to print C. So now C can be printed here, right? So after printing of the C, then this is making signal S2 up. What does it mean? It is this S2 is becoming now 1. So once this S2 is becoming 1, then this T3 weight of S2, now it is 1. So and here it comes to here, then it becomes 0, means successful wait operation. After this successful wait operation, it is printing A. After that, it is making signal of S1, means again the control comes to T2. So now this T2 can execute again this S1. What is the S1 value here? 1. So now this S1 value becomes 0, then it is printing B. So this is way, first the execution is started with the T2, then we went to the T1, then we went to the T3, right? So this is the execution order. So if you want to get the output string BCA, 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 the execution order of these three threads should be like this. So, and if you verify, if I want to block T1 and T3, I should allow a wait operation on a semaphore whose initial value is 0. So, for this T1 and T3, the S3 value and S2 value must be 0. And S1 value should be 1 because we need to allow this T2 to print B. So hence we can say that S1, the initial value of semaphore S1 is 1, the initial value of semaphore S2 is 0, the initial value of semaphore S3 it is 0. So for this initial values of S1, S2 and S3, this particular output string is possible. BCA, BCA, BCA type of output string can be possible with this combination, right? So S1 is equals to 0, S2 is equals to 0 and S3 is equals to 0. With this combination only T2, T2 can print first B, then this T2 can give a chance to the T1 to print C, then this T1 can give a chance to the T3 to print S2, to print this particular A. So this is the way how T1, T2, T3 threads are keep on rotating, and they used to, rotating in the sense they keep on executing continuously and they keep on print the output order like BCA, BCA, BCA and so on. So this printing is possible with these initial values. So verify these initial values in which options we are having. S1 is equals to 1, S2 is equals to 0 and S3 is equals to 0, which is the correct answer. Okay, so this is what the explanation for this question. So I believe you are clear with the explanation of this. Let's move to next question. So coming to this question, this is the question we have from operating system subject in GATE 2022 examination based on deadlocks concept. Look at the question statement. Which of the following statements is a true with respect to deadlocks? Option A, circular wait is a necessary condition for the formation of deadlock. Yes, it is true. Necessary condition but not sufficient. It is necessary condition. Then what are the other necessary conditions for occurrence of deadlock we have in the system? There are 4 necessary conditions for occurrence of deadlock in the system. What are the 4 necessary conditions we have? The first one is mutual exclusion. Next one is hold and wait. And the next one is no preemption. And the next one is circular wait. So these are the 4 necessary conditions for occurrence of deadlock in the system. Okay, so if all these 4 are occurred simultaneously in the system, then we can say that the system is in deadlock state. So circular wait is a necessary condition. Of course, it is the correct statement. It is a necessary condition but not sufficient condition for formation of deadlock in the system. Hence, this condition is, this statement is true. Then coming to the option B. In a system where each resource has more than one instance, comma, a cycle in its wait for graph indicates the presence of deadlock. So is this condition is true? No, this condition is false. So why this condition is false? Because wait for graph and each resource has more than one instance. So basically this wait for graph is used for, basically this wait for graph is used for detecting the deadlock when the resource has single instance. So when the resource has single instance, then in order to detect the deadlock, we consider this particular wait for graph. But here what it is mentioned, each resource has more than one instance. It is not the correct. If it is more than one instance, means multiple instances are there. So if multiple instances of resource type we have, then to detect the deadlock, we have one algorithm called resource request algorithm. But this wait for graph is used for only for, so this wait for graph is used for only one instance per resource. But resource request algorithm is used for when a resource has multiple instances. Both are used for deadlock detection only. Okay. So, but here what is the question statement? What is the statement of B here? Where each resource has more than one instance, a cycle in its wait for graph indicates the presence of deadlock, in the sense false, because this wait for graph is applicable for single instance per resource. Single instance per resource. Single instance per resource. Okay. Right. Next, look at the option C. If the current allocation of the resources to processes leads the system to unsafe, then the deadlock will necessarily occur. If the current allocation of resources to a process leads to the system to the unsafe, then the deadlock will necessarily occur. What is the correct answer here? So you know that this particular statement is false. How you can say that false? Because very simple statement. A deadlock state is always unsafe. A deadlock state is always unsafe. A deadlock state is always unsafe. But all unsafe states, all unsafe states, okay, all unsafe states, all unsafe states may or may not lead to the deadlock. May or may not lead to the deadlock. Deadlock state is always unsafe state, but all unsafe states may or may not lead to the deadlock. So based on this statement, you can say this option C is false statement. Then we have option D. What is option D here? In the resource allocation graph of a system, if every edge is assignment edge, what is that assignment edge? Assignment edge in the sense from resource to process, right? From resource to process. This is what your assignment edge. Process P, let's say. This is your assignment edge. Allocation edge, you can also call it as. In the resource allocation graph of a system, if every edge is assignment edge, then the system is not in deadlock state. Is it true? Yes, it is true. How we can say that it is true? Because every process is getting satisfied with the assigned resource. There is no process which is having further requirement. Every process is having only one allocation. There is no request. So means that whatever allocation is there, with that allocation every process can finish, so that there is no chance of deadlock. Hence you can say this statement D is true. So overall, if you verify, option A and option D are true, so that the answer for this question is A and D. The answer for this question is A and D. So this is the way how we can answer this particular question. So I hope you are clear with the explanation of this. Thank you. So this is the question we have from OS subject in GATE 2022 examination. Look at the question statement. Which one of the following statement is false? So we need to find out the false statement here. Option A, it is given that TLB performs an associative search in parallel on all its valid entries using page number of incoming virtual address. Option B, if the virtual address of a word given by CPU has a TLB hit, but the subsequent search for the word results in a cache miss, then the word will always be present in the main memory. Option C, the memory access time using a given inverted page table is always same for all incoming virtual addresses. Option D, in a system that uses hashed page tables, if two distinct virtual addresses V1 and V2 map to the same value while hashing, then memory access time of these addresses will not be same. So this is what the question statement. We need to find out the false statement here. So let's consider first option A. Option A, it is saying that the TLB performs an associative search in parallel on all its valid entries using the page number. See, it performs searching, some parallel searching it is doing on all its valid entries using the page number. Is it correct or not? Verify. If you consider the TLB page table, the TLB entries, I mean the TLB table, if you verify, TLB contains what? The TLB contains most referenced page numbers along with the frame numbers, right? So the TLB contains the most referenced page numbers along with the frame numbers. So using the page number, it is performing some parallel search, right? It is performing some parallel search, and the same it is given in the question statement, right? So hence this particular statement is true. Look at the next option B. If the virtual address of a word given by the CPU has a TLB hit, this is the crux of this question, TLB hit, but the subsequent search for the word results in a cache miss, then the word will always be present in the main memory. Is it true? Yes, it is also true statement. So why it is true statement? Consider the same TLB table. So it is saying that if the virtual address of a word is word given by the CPU has a TLB hit in the sense it is part of the TLB table. So if it is part of the TLB table, what is the TLB entry? TLB entry is page number and the frame number. So this frame number is what? It is related to the physical memory. If it is a hit in the sense, obviously it is also part of the main memory. Yes or no? Because frame number is also part of the TLB, right? So if the TLB hit is occurred, the corresponding, the virtual address of the particular word will always be present in the main memory is a true statement here, right? Next, option C, if we verify, the memory access time using a given inverted page table is always same for all incoming virtual addresses. Is it true statement? No, this is false statement. So why it is false statement? Because this inverted page table or else this inverted paging concept, it is not doing any hashing indexing scenarios. So that is why this particular statement is false. Then coming to the option D, in a system that uses hashed page table, if two distinct virtual addresses V1 and V2 map to the same value while hashing, then the memory access time of all of these addresses will not be the same. Is it true statement? Yes, it is true. Reason, while we are applying hashing, if two distinct virtual addresses V1 and V2 map to the same value, then the memory access time of these addresses will not be the same because of there is a possibility some entries can be part of the end of the linked list, right? So that is why this particular statement is true. So overall, as the question is asking us to find out the false statement, option C is the false statement here, because inverted paging concept is not using any indexing mechanism. So that is why this will be, whatever the memory access time using a given page table is always same for all incoming virtual addresses is false statement here. Okay, so hence option C is the correct answer for this question, right? So let us look into next question. So this is the question we have from again operating system, which is part of GATE 2022 examination. Look at the question statement. Consider two file systems A and B that use contiguous allocation and linked allocation respectively. A file of size 100 blocks is already stored in A and also in B. Now consider inserting a new block in the middle of the file, that is between 50th to 51st block, whose data is already been available in the main memory. Assume that there are enough free blocks at the end of the file and that the file control blocks are already in memory. Let the number of disk accesses required to insert a block in the middle of the file in A and B are NA and NB respectively. Then the value of NA plus NB is. So look at here what you are doing. You are performing two file allocation techniques. One is contiguous file allocation technique, another one is linked file allocation technique. So if you consider first linked allocation technique, this linked allocation technique, what it is contiguous manner, right? It is sequential access. So we are having 1 to 50, first 1 to 50 disk blocks must be accessed. First 1 to 50 disk blocks must be accessed because you are inserting a new block between 50th block and 51st block. So that is why compulsory we have to access these 50 blocks first. After accessing these 50 blocks, then 50 and then we are having 51. In between these two we are inserting a new block. So whenever we are inserting a new block here, so for this it is requiring one access, and for accessing of all these 50 blocks it requires 50 accesses, and this particular new blocks related we need to link this one and we need to link this one, right? So 50 you need to access, and this new block access means this has to be linked with this and this has to be linked with this, correct? So means that for this it is having one and for this it is having one more. So this, you know that linked list in the sense, this is what data field and this is what your address field. This address field is pointing to this one, means that you need to link this one, you need to link this 50th block to the new disk block, and as well as part of this new disk block you are having again data portion and address portion. This address portion must be linked with this 51. So for this one and for this one access extra, so that for linked list you are considering 52 number of accesses. And coming to the contiguous, so if we consider for contiguous, if we consider for contiguous, so contiguous, what will happen in this also, 1 to 50 first we are having, then we are having 51 to 100, right? So total 100 blocks it is saying, right? So then between this 50 and 51, I need to insert the, I need to insert a new block here. So for insertion of this new block between 50 to 51, so it means that the 51st, so whatever the 51st we are having, that data should be shifted to the 51 and 52, and this 51 should be shifted to 52, and this 52 should be shifted to 53. So like that, the 100th one should be shifted to 101. So it means that all these 51 to 100 number of blocks, which are 50 blocks, must be shifted right. So they have to be shifted to the right in order to accommodate the new disk block, right? So it means that we need to access this 51, and then again we need to read this one. After that, we need to write this 51 to the 52. Then the 52 we need to read, and we need to perform writing to the 52. Then 52 we need to read, and this 52 data need to be copied into the write into the 53. So this is the way every disk access, every disk can take two accesses. One is for read access, another one is for write access. So total 50 into 2, 100 accesses it is required, and the new disk we are inserting here, right? The new disk block we are inserting. So total here you are having one disk access. So 101 plus 100 plus 1, total 101 number of disk accesses are required for your contiguous, and for linked access you required 52. So 101 plus 52, which is going to be 53. 153 is the answer for this question. So I hope you are clear with the explanation of this. Okay, thank you.